Welcome. Today, we are looking at rates of chemical reactions. This is a key topic in your chemistry exams for SS2. Pay close attention. Let us begin. First, let me explain what the rate of a chemical reaction is. The rate of a chemical reaction is the speed at which reactants are converted into products. It is the change in concentration of a reactant or product per unit time. A fast reaction happens quickly. For example, the explosion of hydrogen and oxygen is very fast. A slow reaction happens slowly. For example, the rusting of iron is very slow. The rate of a reaction is important in many fields. It determines how quickly a product can be made. It affects the cost of industrial processes. It influences the shelf life of foods and medicines. Understanding reaction rates helps chemists control reactions. They can speed up useful reactions. They can slow down unwanted reactions. Now let me explain how to measure reaction rates. There are several methods. The rate can be measured by monitoring the disappearance of a reactant. The concentration of the reactant decreases over time. The rate can also be measured by monitoring the appearance of a product. The concentration of the product increases over time. The rate is the change in concentration divided by the change in time. The units of rate are mole per cubic decimeter per second. For example, if the concentration of a reactant decreases from 0.5 moles per cubic decimeter to 0.3 moles per cubic decimeter in 10 seconds, the rate is 0.2 divided by 10. This gives 0.02 moles per cubic decimeter per second. Different methods are used to measure rates. These include measuring gas volume, measuring mass change, measuring color change, and measuring pH change. The choice of method depends on the reaction. Now let me explain the factors that affect reaction rates. The first factor is concentration. Increasing the concentration of reactants increases the rate of reaction. This is because there are more particles per unit volume. The particles collide more frequently. More collisions lead to more successful reactions. For example, the reaction between hydrochloric acid and marble chips is faster with more concentrated acid. The second factor is temperature. Increasing the temperature increases the rate of reaction. This is because the particles have more kinetic energy. They move faster. They collide more frequently. They also collide with more energy. More collisions have enough energy to overcome the activation energy. The rate of reaction approximately doubles for every 10 degrees Celsius increase in temperature. For example, food spoils faster at room temperature than in a refrigerator. The third factor is surface area. Increasing the surface area of a solid reactant increases the rate of reaction. This is because more particles are exposed. There are more sites for collisions. For example, powdered marble reacts faster than large chips of marble. The fourth factor is catalysts. A catalyst is a substance that increases the rate of a reaction without being consumed. It provides an alternative pathway with a lower activation energy. Catalysts are very important in industry. They speed up reactions without being used up. For example, iron is used as a catalyst in the Haber process. Enzymes are biological catalysts. They speed up reactions in living organisms. Now, let me explain the collision theory. The collision theory explains how reactions occur. It states that for a reaction to occur, particles must collide. They must collide with the correct orientation. The particles must be properly aligned. They must also collide with sufficient energy. The minimum energy required for a reaction to occur is the activation energy. Only collisions with energy equal to or greater than the activation energy result in a reaction. Collisions with less energy do not result in a reaction. They are ineffective collisions. Increasing the temperature increases the number of particles with sufficient energy. Increasing the concentration increases the number of collisions. Increasing the surface area increases the number of collisions. A catalyst lowers the activation energy. This allows more collisions to be successful. The collision theory explains all the factors that affect reaction rates. Now, let me explain the concept of activation energy. Activation energy is the minimum energy that particles must possess for a reaction to occur. It is the energy barrier that must be overcome. The higher the activation energy, the slower the reaction. The lower the activation energy, the faster the reaction. A catalyst lowers the activation energy. It provides an alternative pathway. The reaction still goes from reactants to products, but it goes over a lower energy barrier. The activation energy can be represented on an energy profile diagram. The reactants are on the left. The products are on the right. The top of the curve is the transition state. The difference in energy between the reactants and the transition state is the activation energy. The difference in energy between the reactants and the products is the enthalpy change. An exothermic reaction releases energy. The products have lower energy than the reactants. An endothermic reaction absorbs energy. The products have higher energy than the reactants. Now, let me explain the effect of catalysts. A catalyst is a substance that increases the rate of a reaction without being consumed. It works by lowering the activation energy. It provides an alternative pathway. The catalyst is not used up in the reaction. It can be used again and again. Catalysts are very important in industry. They allow reactions to occur at lower temperatures. This saves energy and money. They allow reactions to occur faster. This increases production. Catalysts are also important in biology. Enzymes are biological catalysts. They speed up reactions in living organisms. Without enzymes, life would not be possible. Catalysts can be homogeneous or heterogeneous. A homogeneous catalyst is in the same phase as the reactants. A heterogeneous catalyst is in a different phase. For example, the Haber process uses an iron catalyst. The iron is solid. The reactants are gases. This is a heterogeneous catalyst. Now, let me explain the rate law and order of reaction. The rate law is an equation that relates the rate of a reaction to the concentration of reactants. The rate law has the form rate equals K times the concentration of A raised to the power of M times the concentration of B raised to the power of N. K is the rate constant. M is the order with respect to A. N is the order with respect to B. The overall order is M plus N. The order of a reaction can be determined experimentally. It is not determined by the stoichiometric coefficients. For example, the reaction between hydrogen and iodine has the rate law rate equals K times the concentration of H2 times the concentration of I2. The reaction is first order with respect to hydrogen. It is first order with respect to iodine. The overall order is second order. The rate constant K depends on temperature. It increases with increasing temperature. The Arrhenius equation relates the rate constant to temperature. It is K equals A times e to the power of negative EA over RT. A is the frequency factor. EA is the activation energy. R is the gas constant. T is the temperature. The Arrhenius equation shows that the rate constant increases exponentially with temperature. Now, let me explain the effect of concentration on rate. For a reaction, the rate is proportional to the concentration of the reactants. The relationship can be expressed as rate equals K times concentration to the power of N. If the rate is directly proportional to the concentration, the reaction is first order. If the rate is proportional to the square of the concentration, the reaction is second order. If the rate is independent of concentration, the reaction is zero order. The order of a reaction must be determined experimentally. The half-life of a reaction is the time required for the concentration of a reactant to decrease by half. For a first-order reaction, the half-life is independent of concentration. For a second-order reaction, the half-life is inversely proportional to concentration. The half-life is a useful concept in kinetics. Now, let me explain the effect of temperature on rate. Increasing the temperature increases the rate of reaction. The rate constant increases with temperature. The Arrhenius equation describes this relationship. The activation energy also affects the rate. Reactions with high activation energies are more sensitive to temperature. They increase more with temperature. Reactions with low activation energies are less sensitive to temperature. They increase less with temperature. The rule of thumb is that the rate doubles for every 10 degrees Celsius increase in temperature. This is true for many reactions near room temperature. However, it is not exact. The exact relationship is given by the Arrhenius equation. Now let me explain the effect of catalysts on rate. A catalyst increases the rate of a reaction by lowering the activation energy. It provides an alternative pathway. The catalyst is not consumed. It can be used again. Catalysts are specific to particular reactions. They work by forming intermediate compounds. The intermediate compounds then decompose to give the products and regenerate the catalyst. Catalysts are used in many industrial processes. The Haber process uses an iron catalyst. The contact process uses a vanadium pentoxide catalyst. The catalytic converter in cars uses platinum and rhodium. Enzymes are catalysts in biological systems. They are very specific. They work under mild conditions. They are essential for life. A common exam question asks you to explain the factors affecting reaction rates. Here is a sample answer. The factors affecting reaction rates are concentration, temperature, surface area, and catalysts. Increasing concentration increases the rate. Increasing temperature increases the rate. Increasing surface area increases the rate. Adding a catalyst increases the rate. These factors affect the number of collisions and the energy of collisions. The collision theory explains these effects. Another exam question asks you to define activation energy. Here is your answer. Activation energy is the minimum energy that particles must possess for a reaction to occur. It is the energy barrier that must be overcome. A catalyst lowers the activation energy. This increases the rate of reaction. The activation energy is represented on an energy profile diagram. It is the difference in energy between the reactants and the transition state. Another exam question asks you to explain the Arrhenius equation. Here is your answer. The Arrhenius equation relates the rate constant to temperature. It is K equals A times e to the power of negative EA over RT. A is the frequency factor. EA is the activation energy. R is the gas constant. T is the temperature. The equation shows that the rate constant increases exponentially with temperature. It also shows that reactions with higher activation energies are more sensitive to temperature. Let me give you a quick summary. The rate of a reaction is the speed at which reactants become products. Factors affecting rate include concentration, temperature, surface area, and catalysts. The collision theory explains reaction rates. Activation energy is the minimum energy for a reaction. Catalysts lower activation energy. The rate law relates rate to concentration. The Arrhenius equation relates rate constant to temperature. Practice these concepts. When you have them down, move to topic 4.